we're on the x-axis. So this is the x-axis right here. We're on the x-axis. Is the total voltage 0? Okay. And B, where is the total voltage? And then we can say some voltage. Where's the total voltage equal to let's say 20 volts, positive or negative 20 volts on the x-axis. So just similar to what we did with electric field, where we said, where's the electric field equal to a certain number? So where's the voltage equal to, we could say, either plus 20 volts or minus 20 volts on the x-axis. Where on the x-axis is the voltage 0. And then what else did we ask? Oh, we could say, what is the potential energy? What is the potential energy of this two-charge? What is the potential energy of this two-charge configuration? Okay, and what else? What is the total voltage? What is the total at some random point? So we could say, what is V total at let's just say 1.4 meters. Okay, then if I feel the need, then we can add more questions as we proceed. So where on the x-axis is the total voltage 0. With voltage, it's a bit, of course, it's quite a bit easier to answer these. You don't have to worry about direction. So if you choose a certain place, like let's say here, and it has components x0, well, as long as the distance is appropriate, probably closer to the -2, the voltage could be 0, but it could also be 0 on the other side. So since you're not worrying about direction, these are the voltage created by each charge is just simply a scalar, right? So the voltage created by this and that, they add up like a basic number. So then we're just going to say at some random point, the voltage due to this charge needs to equal the voltage, or we could say this way, voltage 1 plus voltage 2 is 0. So 9 times 10 to the 9th, -2 times 10 to the -9 over x. So then the distance between here and here is going to be x minus -3, the distance equation, right? So it's just this minus this. And I'll just put for now absolute value of that. Right, absolute value of the distance. then plus the voltage of this guy, 9 times 10 to the 9th, 5 times 10 to the minus 9 over x minus absolute value of x minus 2. And then that's equal to 0. Okay. And then this one will cancel this one will cancel this. Actually, the 9 can disappear since it's we're setting it equal to 0. So even that can go. So then we'll just have negative 2 over absolute value of x plus 3 plus 5 over absolute value of x minus 2 is equal to 0. And then we can set this into a solver. Okay. Yeah, I see that makes sense because one of them is on this side of the charge, right? So that is what here? Negative 19 thirds, negative 11 sevenths. It's not telling us the coordinates here. Oh, okay. So negative 19 third, that's going to be negative. So there's one here. Let's see if this is negative 1.57. That means it would be around here, right? Okay. And a 6 would be way over there on the left side. You see? So, but actually what ends up happening is that this is an equipotential surface. Remember yesterday in the simulation that I showed you guys? So this is actually like this. Everywhere there, the voltage is 0 volts. So there's always going to be 2 points on the x-axis where it satisfies that condition, because it's going to go like this, you know. So later on, we can come back to that and maybe even try to solve the equation of that equipotential surface. You see? Okay, so the question B, where is the voltage 20 volts, let's say, or negative 20 volts? So now anything closer, the negative 20 volts is going to be like somewhere like this. You know, anything inside of that circle is going to be, we're going to be going into a valley, right? The equipotential surfaces like this. So I'm expecting somewhere here, somewhere there to be negative 20 volts. Positive 20, it's probably going to look something like this. Probably not that close to the 5, maybe something like this. So there might be 2 answers there then. There's going to be 2 answers there. Okay, so then how would we do that? So then just kind of proceed similar to this, except don't get rid of the 9. Write it as negative 18 over absolute value of x plus 3 plus 45 over absolute value of x minus 2. And then that's equal to, so then let's set it equal to negative 20, let's say. Negative 20. See, for that one, since it's not equals to 0, you can't get rid of the 9 here. So you want to keep the 9, multiply it with the 2, 18, and then 45. Okay, now let's set that equal to negative 20. So I'm expecting the answers to be close to the negative charge.
That's for B, correct?
Yes, B. Yep. So 9 times 2, 18. 9 times 5, 45. And then negative 20. Well, don't tell me I have to calculate that. Give me a decimal answer.
Professor, maybe if you click approximate forms, it might give you the number.
What do you mean?
The button where it says approximate forms.
Oh, is there? Where is that?
Yeah, go back down to the answer.
Oh, yeah, yeah. Okay, I see what you mean.
Yeah.
Oh, there you go. Okay, nice. Negative 2.4. Yep, yep. Yeah, negative 2.4. Okay, so let's write that down. Negative 2.404. Negative 3.643. Yeah, so that means negative 2.4. Oh, that's pretty close. Yeah, that's pretty close to the negative charge here. And then negative 3.6. Oh, that's very close. Negative 3.0. I'm surprised it was that close. So basically, it's 0.6 meters from the charge. 0.6 meters from the charge either way.
Professor, how'd you get negative 18 and negative 4 plus positive 45?
Oh, because 9 times 2, 18, and then 9 times 5. On the other one, I had canceled the 9 because it was 0.
Oh, okay.
Yeah, but here I can't get rid of the 9.
Got it.
Probably would have been good. I mean, even in this case, you could keep it if you want, set it equal to 0, because it's not going to change this answer. And then use that same equation here, but then just set it equal to this voltage. You could even do it that way. Yeah. Okay, so yeah, I didn't realize it's going to be very close, like this kind of. You see. Okay, now the positive 20, we just go back to it. .239, so this is for the positive, 0.239, and then 3.99. 0.239. Oh, so it kind of starts 0.239 would be somewhere here. And then it goes like this. 3.99 goes all the way to like somewhere here. So it looks very different than the negative 20. Negative 20 is crunched up there, very small, 0.6 meters, 0.6 meters from that charge. The positive 20 looks so different. It was like this. You see, so these are like I told you yesterday, they're like topographic maps that show you the elevation. So these are called potential surfaces, equipotential surfaces. And they're the closest thing you can have to topographic maps. Okay, so now C would be quite a different kind of question. So this was B. Is a potential energy question. So what is the potential energy? So that's kind of more like asking the ionization energy again, right? So how much energy to separate them? So this one, K, Q1, Q2 over the distance between them. With two charges, it's easy, of course. There's just two charges to worry about. So 5 times 10 to the minus 9. Negative 2 times 10 to the minus 9 over their distance was 5 meters. So I'm putting the negative in for voltages and electric potential energy. You always put the sign of the charge. Okay, so then this cancels this, and then you go 5 cancels the 5, and then you get negative 18 nanojoules. So that's the potential energy of the two charge configuration. And if it tells you how much energy do you need to separate them, then that would be 18 nanojoules, right? Okay, so then total voltage at some random point, okay? Again, this is going to be very easy compared to the electric field, right? Total voltage at some random point. So then it's just going to be at 1,4. So that would be somewhere here, right, on the graph, 1,4. So then you're just going to do the voltage due to this. So what's that going to be? So if it's 1,4, one would be midway. So more like midway. Okay, anyway. So then this distance would be 1. And then this distance would be 4. Right? And then so this distance would be square root of 17. With voltage, this is the only thing that's important, the distance, because you don't have to worry about cosine sine. And then this distance would be what? So 1,4, would be 4. What would the horizontal distance be? Well, if it's 1, and this is negative 3, this would be 4. So then that's 4 root 2. Right? So then those distances is what I'm going to use, but I'm also going to use the sign of these charges. So the total voltage is going to be 9 times 10 to the 9th. Then it's going to be 5 times 10 to the negative 9 over square root of 17, right? Plus 9 times 10 to the 9th. And negative 2 times 10 to the negative 9 over 4 root 2. And then this cancels this cancels this. So 45.
You got 17 by doing the triangle?
Yes, to do the hypotenuse. It was a 1,4. It was a 1,4 triangle. So square root of square this and square that. Yep.
1, 4.
So square root of 17 minus 18 over 4 root 2.
And then the 4/2 is also the triangle, right?
Yeah, well, that's since it's a 4/4, it would be a 45-degree angle. So it's a 45-degree triangle. So then it just 4√2. Yeah, I mean, because it's a 1, 45-degree triangle is a 1√2. So if this is 4/4, and then this is 4√2. Yep. Okay, so 45 divided by 17 square root minus 18 divided by 4 divided by 2 square root. Okay, 7.732 volts. Again, that would be part of, see, 7 volts. Yeah, that makes sense because if it's way over there, it's probably part of a equipotential that's coming like this. You know, so it goes, encompasses like this, right? So everywhere there would be 7 volts like that, goes over there like that, you see. So then if this was the 20 volts, the positive 20, it would make sense that this would be a lower voltage, you see, lower voltage than that because it's a bigger circle, you see. So it's kind of like I'm always envisioning those equipotential surfaces like that. Okay, what else can we ask? Well, we could go back to the first part and say, find the equation of the surface that has an equipotential of 0. Find the equation of the surface. I'm referring to them surface because they're kind of actually 3D, you know, but we could just find a 2D plane equation. We don't have to work in 3D necessarily. So find the equation of the surface of voltage equal to 0. So then what we do? So let me get a fresh paper. Going to be the voltage of xy is going to be the distance equation. What was this? -2, 0. And the other one was, no, sorry, -3, 0. And then the other one was 2, 0. So then you're going to have here 9 times the 5. No, sorry. 9 times the -2. Over. Okay, so since we're at the, we're not necessarily on the x-axis anymore, so we're going to use the general distance equation, x plus 3 squared plus y minus 0 squared. Right, so then square root of that, okay, plus 9 times 5 over square root of x minus 2 squared plus y squared. And now if we're trying to find this, the equation of the surface where the voltage is 0, then we just put this equal to 0. And we want to solve for the relationship between y and x. It's probably a circle, right? It looks like a circle, but it might be ellipse. Well, let's find out. Okay, so then the 9 cancels. So what do we do with this? We can take this to the other side. if we square both sides, we get rid of the radical, right? So it'll be 25, and then cross multiply. So it'll be 25 times x plus 3 squared plus y squared is equal to 4 times x minus 2 squared plus y squared. Right, so square this, square this. Square this, you just get rid of the radical. Square this, you just get rid of the radical. Then multiply into 25. So you have x squared plus 6x plus 9 plus y squared is equal to 4x squared minus 4x plus 4 plus y squared. Okay, then multiply into 25. 25x squared plus 6 times 25. That's going to be 150, right? 150x plus 9 times 25. That's going to be 225. 225. Plus 25y squared. 4x squared minus 16x plus 16 plus 4y squared. Does this resemble anything that you've done back in math class? Well, it soon will. Maybe you don't really see where I'm going with this yet, but it soon will. Let's see here. Subtract 4x squared from both sides, so 21x squared. Then bring this, add 16x to this side, so 166x. 225 minus 16, that's going to be 209. 25 minus 4, 21. 21y squared. So then divide this by, well, I guess, yeah, we could divide everything by 21. Let's see, get my calculator. $66 divided by 20. $7.90476x. 209 divided by 21. 9.95238. And then this is y squared. Okay, then we can take this to the other side. Negative 9.95238. Okay, do you remember the step, the process called completing this, completing the square? So if I want to make this a perfect square, what do I do? In other words, this ultimately comes down to trying to find the equation that defines this line. So as you are working through this, you know, so since the power of the coefficient of the y turns out to be the same as the coefficient of the x squared, I mean, you see, the coefficient of the x squared turns out to be the same thing as the coefficient of y squared. That means this is a circle, you see. So then when I divide everything by 21, you have this, then you have this. So a circle is developing here. Okay, so then I took this piece to the other side and wrote it as -9. Then I'm going to take half of this value and square it and add it to both sides. Half of this and square it. So 7.90476. I believe it was called completing the square, right? In math, in intermediate algebra. Probably you haven't done that in a long time, so you've forgotten it. Yeah, Daniel? I've forgotten the term, but I believe it's called completing the square. And it's something we've done probably in intermediate, maybe never reused it again. In calculus class, you don't really do it, do you? It doesn't come up that often, I think. So half of the 7.9, 3.95. Then square that. But this is an important number to remember, so I'm going to write it down here. Half of this is 3.95238. Then square that. Okay, so now add 15.6213 and then add it to the right side. Yeah? Then subtract from this 9.95, so I can just basically keep it on the calculator and then go minus 9.95, 238. And then you got this thing. So then what's this? It's going to be a perfect square, right? It's going to be like this, x plus, and then what's going to go here? By perfect square, I mean x plus something squared, right? It ends up being half of this, right? Goes here, which is this. That's why I wrote it on the side. 3.95238. Plus y squared. You see? So then when you expand this out again, the way to expand it out is to square this, x squared, and that you get that. Then you double this, right? Which you get that.
Where'd you get the 15 from?
Huh?
The 15.
Say that again?
Where did you get that 15 one from?
By having this, halving it, which you get that, but then squaring that.
Oh, it's the b over 2.
Yeah, you got it. B over 2a. No, not b over 2a. Yeah, b over 2.
Square.
Yeah, the idea is when you have x plus a squared, it's x squared plus 2xa plus a squared, right? So what I'm trying to do here is to say, oh, what number do I need here so that this becomes a perfect square? So then I say, get rid of this, put it on the other side. Then I say, take half of this, then square it. As long as you do it to the other side, you can do anything to the left side, you see. To the left side of the equal sign, as long as you do something here, you could do the same thing to the other side. So then the number that I choose here is this a squared, right? Because I want to make it into something like this, right? So I've got essentially, basically, I've got this portion already. So imagine I'm missing the a squared. You see, I've got this portion, which is this. So then I say, in order to know what goes there, divide this by 2. When you divide that by 2, you get A. You see, the X is already this guy, you see. So you just divide this by 2, so you isolate the A, and this is the A. You see, such a clever technique, man. That's amazing. You probably didn't pay attention to that, but now it's beautiful. So then you square that, and that provides you the A squared, the missing piece that you need. But then you have to add it to the right side. So then when you add it here, you subtract this from it, you get that. Okay, then you get an equation for a circle. So what is the radius of that circle and the center of that circle? So we now know what that shape's going to look like. The center of the circle is negative 3.95. Ah, you see that? So it's off-centered. It's not centered on this charge. This is the center. Negative 3.95. It's a bit to the left, huh? Yeah, it doesn't have to be centered. And what's the radius of it? It'd be this square root of this, right? Would be the radius of that. Because it's the equation of a circle, x plus h squared plus y squared is equal to r squared. So the square root of this would be 2.38. So it would be 2.38 squared would give you that, right? So then the radius of this circle is going to be 2.38 meters. Does that make sense? What was the point that we had found that was remember the question A? Well, 2 points. Oh, okay, we had found that this point was negative 1.571, right? Negative 1.571. And then this point was what? Negative 6.33. So does that make sense? If the center is negative 3.95, right? If the center is negative 3.95 from here, right? Negative 3.95, would that make sense that the radius is 2.38? In other words, if I go one radius any direction, that should give me anywhere. So if I add 2.38 to negative 3.95, what's going to happen? 3.95 negative. So then if I add 2.38, yep, there you go, negative 1.57. See, if I go this way, right, then it gets me over there. If I go this way, so then what would I do? 3.95 negative minus 2.38. Okay, negative 6.33. Cool. So that confirms our answer. If the center is negative 3.95 with a radius of that goes in any direction, that gets you to the 2 points that you had found. Cool. Okay, let's see what else. Okay, one thing I want to show you also from this problem is how we can use voltage to go back and find electric field.